Oh, hey everybody, and thanks for the introduction, Andrew. It's a great pleasure to be here. Hopefully, everybody can hear me well, and you can see my slides too. It's a pleasure to talk to you today, and I would like to tell you a little bit more about some thoughts about what I think about is coming beyond the metaverse. Like, what does that even mean? So everybody's talking about the metaverse, and the metaverse is a really interesting concept. It creates digital spaces to meet people. It hopefully enhances communication for the better. It enables new forms of entertainment. And also AR is really something that can help augment human vision. So there's a lot of potential, and it's a really exciting time for computer graphics, really. Like, I've been part of the computer graphics community for the last 20 years now. And I mean, it's been around AR, VR as a technology for a while, but I think now is a great place and time to really push this one level forward. What I'd like to think about is not just how XR enables the obvious applications that everybody talks about, but thinking a little bit more about the human perspective of this and how to create perceptually realistic experiences that are also visually comfortable. And many of you are working on different aspects of this, so hopefully you get some interesting insights from this talk. Obviously, if we want to talk about perceptual realism and user comfort, we need to understand the user. And the primary interface between an XR experience and the user is typically the display. So the first thing that we need to think about a little bit more is the eye. And many of us, including Angel and others, have been thinking about, how do we understand the distribution of photoreceptors on the retina, for example, to help design better graphics experiences and display systems. The photoreceptors are pretty dense on the fovea. They get less dense farther away in the periphery of the visual field. So we can use techniques like foveated rendering, for example, foveated displays. These are all fairly, standard techniques that have been around the community for a while, but there's a lot more to explore still. And this is an interesting aspect. But there are other things about the human eye that are worthwhile thinking about. So one other aspect is the accommodation mechanism. So how does the lens, the crystalline lens in the eye, accommodate to different distances? And how does that enable different types of, affordances and experiences? How does refractive errors and prescription in the human eye, how are those affected by the display, by the rendering experience? How do we make sure that the person gets the best experience with great visual clarity and the ability to accommodate at different distances? But we also need to study eye movements in general. If we want to enable gaze contingent paradigms, which is a big thing in, high performance graphics for XR, then we need to think about not only building technology that robustly tracks these eye movements, but then also in rendering and display techniques that are able to leverage that information. Okay, so I want to talk a little bit more about these different aspects. And I mentioned perceptual realism and visual comfort as two key aspects of, let's say, our research that we focus on, but that are generally very important. So for human-centric displays. So perceptually realism, what does it mean? Like, think about it this way. If you have a mixed reality experience, we want to design this in a way that, fools the user in believing that the digital content is absolutely real. So in computer graphics, we've been calling this, photorealism, and we've achieved that maybe a few years ago. We can create images that are indistinguishable from reality. But there's a difference between photorealism in computer graphics and perceptual realism in VR and AR. Perceptual realism includes aspects that include, your eyes accommodating at different depths, chromatic aberrations, and many, many other aspects, the color matching, the high dynamic range, and other aspects that, are maybe not quite as important for photorealism in computer graphics. So you can think about something like a visual Turing test for displays that we need to pass. And you're probably familiar with the Turing test. So there's a computer and a human person behind a wall. The user only has a terminal to interact with them. And if they can't tell which one is the computer and which one is the person while they're chatting with them, then the computer passes the Turing test. So similarly, for visual Turing test for displays, if we display a virtual teapot augmented on a physical scene, if the user cannot tell which one is digital and which one is physical, then we pass the Turing test. But we're far away from that, and high-performance graphics is one of the key aspects to achieving that, along with display system engineering and other aspects. Visual comfort is important because we want to make sure that people don't get eye strain. They have a visually comfortable experience, and VR and AR is not only for entertainment, for 20-minute games. It is used, for example, for surgery. In the Da Vinci robotic surgery system, the minimally invasive surgery systems, there are thousands of those already performed per year. And the surgeon actually uses an XR system to perform the surgery for hours at a time. So we want to make sure absolutely that there's no eye strain, and it's an absolutely natural and visually comfortable experience. So these are two super important aspects. And then the last thing I mentioned was eye movements. So eye movements include eye tracking, and eye tracking is something that seems like a solved area, like many in graphics, but the devil is really in the detail, and there's no real commercial eye tracking system, especially for AR, that works at the low powers required for all-day wearable use, that is robust enough to drastic changes in the environment, ambient illumination, that has the low latency that captures the eye movements at enough speed and latency to really capture microsaccades and all the subtle eye movements. So it's actually a really big engineering challenge at this stage. And there are some interesting new directions that I want to tell you about in this talk. So my group works on XR technologies mostly, or at least that's one aspect of our group. And that includes AR/VR displays, perceptually driven rendering, and also eye tracking technology in general. So these are some of the topics I want to talk a little bit more about. And there are hopefully some interesting ideas that are relevant to your research in here as well. So let's talk about the display aspect a little bit more. I know that this community doesn't necessarily work on displays a lot, but I think when you work on rendering techniques, keeping the display in mind is absolutely critical, because the two kind of have to go hand in hand. There's the GPU side, there's the rendering algorithm side, and then there's the display side. And sometimes for these emerging systems, it's very difficult to disentangle the three. So it's good to have an understanding of what's out there. To some extent, VR displays today haven't fundamentally changed, at least in their basic principle of operation, from the stereoscopes that were developed by people like Charles Wetzstein in the 1830s. So these are stereoscopic viewing apparatuses where you separate optically the two eyes and you present two different images rendered from slightly different perspectives. So these are stereoscopic displays. And the thing is, they have evolved quite a bit. They've become digital, they've become interactive, they've become shared experiences. But this is a grand challenge. The National Academy of Engineering in the US has declared enhancing virtual reality a grand challenge of the 21st century. So we need to continue to engineer this from all ends, from the optical side, from the electronic side, from the rendering side, from the GPU side. There is so many different challenges, which makes it exciting for us as a research community. One specific aspect that we've been working on in the lab is this idea of making this perceptually more realistic. And one aspect of perceptual realism is to be able to focus your eyes or accommodate them. The challenge was most existing VR and AR displays is that they have a micro display that sits behind a lens. We call this a magnifier design. And what that means is that there's a fixed distance at which this virtual image appears. So you can use the Gaussian thin lens equation or the lens maker's equation on the lower left to predict at which distance the magnified image will appear. To some extent, this is basically just a magnifier lens. There's a lens that magnifies the image, but it also moves it back in depth so that it is appearing at a comfortable distance. For example, something on the order of 2 meters. So the focal length of the lens and the distance between the physical microdisplay and the lens determine, to first order approximation at least, where the virtual image will appear that we actually see. Now, this is a really simple design. It's used by pretty much all commercially available AR and VR displays, but it has a lot of problems. It is a fixed focal plane display, so it doesn't support focus cues. What are focus cues? Focus cues is the inherent ability of your eyes to accommodate or to focus at different distances. So in the real world, we look at different objects at different depths, and our eyes will accommodate to these depths, similar to the autofocus of a camera. And that is really important. It's not just a thing that brings objects in sharp focus and makes them appear sharper with better visual clarity, but it's also important for comfort, because there's this vergence accommodation conflict where our eyes verge, driven by the disparity we render into the images. But if the vergence doesn't match the accommodation, then that creates, nausea, potentially eye strain, and other things. So a lot has been said about the vergence accommodation conflict. I don't want to necessarily go into it too much. I'm just trying to emphasize that accommodation cues are important. So my lab has worked on this for many years, so I'll just give you a brief overview of some of the things we've been touching upon over the last couple of years. There are many different technologies that could be used to address this challenge. Probably the simplest one are gaze contingent varifocal displays. So if you know what distance the user looks at, you could try to adjust the focal plane of the display to exactly the fixation distance or the gaze depth. And this is something that we explored in 2016, 2017. We had the SIGGRAPH e-text. We published a couple of papers at various conferences. And this was also picked up by Facebook, which is now called Meta. The idea is to dynamically change the focal plane. This is think about this as an autofocus mechanism for the display. It's very, very effective, but you do need eye tracking, and it needs to work robustly. There's this idea of using light field displays close to the eye. So the light field in this case would project multiple slightly different images into different parts of your pupil. Very similar to a stereo image where you have one image picked up by each eye optically, but here you want to pick up multiple images over the pupil size of a single eye. And so Magic Leap set out to do that. I consulted with them for a couple of years, and then I co-founded a company called Raxium that was working on micro LED displays for applications like light field displays close to the eye and other applications. So we've been working on these types of technologies. They don't necessarily require eye tracking, and they're really, really interesting. But I've been giving talks about these topics many times, so I would like to focus on a slightly different topic that we've been focusing on in the lab for the last 2 years or 3 years. And that's something that gets me really excited, and that's holographic near-eye displays. So holography has been around for a long time, but it hasn't really become practical until very recently. And this is something that I'd like to share with you about. Holographic displays, you may have seen holograms in museums. Here's a video that I downloaded from YouTube from the MIT Museum. They used to have a pretty good collection of recorded holograms. These are analog holograms. They are optically recorded of physical objects that were physically present at the time of the recording. But what you can see is that a static hologram is kind of like a photographic emulsion that encodes the amplitude and phase of the wavefront at the time of recording. And it has the ability to create high-resolution images over a large field of view with an incredible depth range also. It's really difficult to distinguish between a well-recorded hologram and a physical object. So holograms clearly have the potential to reproduce physical reality in a way that's indistinguishable for a human user. But we need to do this in a digital and interactive way. So what hinders us, or what's been hindering us for the last 60 years since this technology has been around to do that? Well, there's a couple of challenges. The first one is we need spatial light modulators, so small displays that can control the phase of light rather than the amplitude or the intensity. But these have also been available. So when you think about a holographic display that is meant for VR, AR purposes, it would look something like this. You have a laser on the left, like a coherent light source, maybe some collimating optics that creates a collimated beam. That beam illuminates this phase SLM, the spatial light modulator, which delays the phase of the light in a per pixel controllable manner. And so now the aberrated wavefront continues to propagate. And what you basically see is the interference pattern that's created by interference and diffraction in front of the SLM. So, each pixel of the SLM contributes to each point that you actually see. And you need an eyepiece or magnifying glass, basically, to see this, because these SLMs are very small. But that's ideally suited for VR and AR, because this is exactly the architecture of a VR AR display. So holography or digital holograms have the ability to create full three-dimensional images that you can freely accommodate in, and that hopefully at some stage, are indistinguishable from the physical reality. But why are they not physically indistinguishable today? Well, because we don't have great algorithms to compute the phase patterns on these SLMs for some target content. It's a computational display problem, really. And one of the big challenges is that the image quality of holograms, digital holograms, has been low. They can in no way compete with, modern LCD, OLED, or other display technologies in terms of image quality. And one of the challenges, probably the biggest, is this mismatch between the models that we use for simulating the wave propagation inside the display and what actually happens in physics. So there's a model mismatch, a sim to real gap, if you want. And this has been a core focus of our group for the last couple of years. And this is where we developed a set of techniques that we kind of call Neurolography, where we try to combine the best of physical optics and traditional models and modern AI techniques. So I'll just give you, this is a series of papers, and I'll just give you the basic idea in a nutshell, is that we use a camera that can focus at multiple distances, and we capture many pairs of phase patterns that we show on the SLM and intensity images that we record at multiple different depths. This allows us to, train a model that is parameterized by convolutional neural networks, and train the model to model the physical wave propagation that actually happens in the physical optics. And so we don't do this in a black box way. We actually combine traditional simulated models like the angular spectrum method, or ASM, and we only learn the difference between the simulated model and what actually happens in physics. So intuitively, why are the physics different from the simulated model? Well, there are optical aberrations, there are impurities of the source beam, there is electronic challenges in the SLM where you modify one pixel, but the neighboring pixels are also affected. It's actually very challenging to just calibrate this display. And you can think about this neural holography approach where we train this camera calibrated wave propagation model in an automatic way. It's an automatic calibration technique, really. And it gives us a differentiable model that models the wave propagation from phase SLM to any plane in this space in front of it. So this is a pre-processing step that needs to be done once, and then during runtime we can take arbitrary input content such as a 2D image, an RGBD image, a 3D focal stack, or 4D light field, and then supervise this pre-trained model in a way that allows us to estimate the phase pattern from our target content, and hopefully that bridges this gap between sim to real. In the lab, we mainly work on benchtop setups, so they're fairly bulky at this stage, but they show the promise and are starting to be miniaturized as well. So here's a typical benchtop setup for holographic display. There's a laser that's pretty small. It basically has 3 laser diodes, RGB diodes, that are optically combined and coupled into this optical fiber. The fiber brings the light to this, it's just a lens basically that collimates this beam. Here's the SLM, that's a off-the-shelf liquid crystalline silicon phase SLM that we typically use. And then there's a little bit of additional optics that do some optical filtering to clean up the beam. At the end, there's a camera capturing the content, and it can be focused at multiple different depths. So it looks pretty big, but there are clear ways to miniaturize this. We just haven't focused on that in the lab. In this case, I'm just using my cell phone to just peek into this port hole here, where you can see that there's actually an image being formed inside the display. And then, what you get with your traditional methods, traditional phase retrieval methods, like the old school Gershberg-Saxon method that was used to correct the initial Hubble telescope images, the images are noisy, and this noise is basically speckle. Speckle are random interferences of this coherent light that are very difficult to control. And in this case, one interesting thing that I want to point out is that the image is only constrained within the white box. This is from Big Buck Bunny. You've probably seen this movie. But a hologram cannot block any light. You can only redirect the light. So, for any excess light, it needs to redirect it outside the predefined area. So you'll sometimes see funny patterns around the boundary because they're not constrained. And the hologram needs to be able to do that. But typically, you would just block those out. So in 2020, we published our first paper at SIGGRAPH Asia on neural holography, and this idea of calibrating a wave propagation model worked out really well. And we were able to get clips like that. At the time, people were in the physical optics community were really excited about this. This is just a 2D video being played as a hologram, but at the time it was the highest quality RGB hologram that was ever captured. And people were jumping up and down and just adopting these AI techniques for real-time hologram computation. More recently, we've been focusing more on improving these models and also getting 3D results. So at this year's SIGGRAPH, we're actually presenting a paper that's called time multiplex neurolography. So here we use emerging MEMS-based phase spatial light modulators. We have new algorithms, better models. Here are a couple of examples. These are captured results, experimentally captured results of holograms that we capture with our prototype. They look very close to what you may be getting with a traditional amplitude SLM. And keep in mind that we show these phase patterns on the actual SLM, right? They're not really that interpretable because they only modulate the phase. But then when we capture at a slight offset in front of the SLM are these intensity patterns with the camera. And these are all experimentally captured results. I have a great team of students and postdocs who've been working on this. This is not done in real time. This takes a couple of minutes to compute per frame, so it's all pre-computed. But what I'm trying to say is that, if we just look at these results, they get close to, amplitude SLMs, LCOS LCDs. But we can do this with a single pattern on the phase SLM or with multiple time multiplex patterns. There's no mechanical movements, no focus tunable lenses. So this is really interesting. And we're close to bridging this gap in the image quality between holographic displays and conventional displays. But there are other benefits of holograms. For example, in 2020, Facebook, and now Meta described a very thin pancake optic design that uses holographic lenses, which enables to make the form factors thinner, for example. So these use holographic optics. And this year at SIGGRAPH, in collaboration with NVIDIA and Jong-Yoon Kim, we are also showing at SIGGRAPH another VR display design that uses phase SLMs together with a waveguide to enable an ultra-thin VR display that is really in the form factor of eyeglasses. And if you're interested in that, I'll refer you to that paper. But the basic idea is that we can use these phase SLMs and holograms not just to create 3D images, but also to enable entirely new display systems that minimize the form factor compared to existing VR AR displays. They can also be more light efficient because they can reallocate the light. They don't have to block it. They can just reallocate it to regions where they're needed. We can do things like prescription correction, like myopia, hyperopia, but also astigmatism, higher orders. We can do all of that in software. We can correct optical aberrations of the optics and so on and so forth. So this is a really exciting area. And I think it's part of the future of AR and VR displays. Maybe still 5 to 10 years out, I would say. But really interesting direction that is really algorithms driven at the core, which is what makes it exciting for us. Okay, let's move on to some perceptually driven rendering. I think this is something that a topic that some of you have been working on, maybe more so than on the display and physical optics side. So I already showed you this illustration of the human eye, and I'm sure you've seen this a million times. But you've probably thought about, okay, what happens in the refraction, what happens with the photoreceptors, but I want to draw your attention to eye movements again. So when the eye moves, for example, by us just changing our gaze direction, then it rotates. But one interesting aspect that you may or may not be familiar with is that the center of rotation of the human eye, here denoted as C, is actually different from the center of projection. And when I mean center of projection, I think most of you will know what I mean. If you model the eye as a pinhole camera, then it's basically where that pinhole camera sits, or you can call it the no parallax point if you want. But this nodal point N has an offset from the center of rotation. And what that means is that as the eye moves around to gaze at different points of the scene, there's actually some amount of motion, lateral motion of the of this nodal point, of the no parallax point, or the center of projection. And what that implies is that there's a tiny amount of parallax that is induced by ocular movements. And now you may think, okay, this is totally negligible. I have never seen this in my own eye. But that's a really great question, and that's what we start out with. Is this effect even noticeable? Is it noticeable in VR? And can we dial it into the rendering part if we had eye tracking to improve something? So it turns out that this effect actually in the vision science community is known as ocular parallax. It's this tiny amount of parallax that happens as the eye shifts, and it is enhanced on the right here for rendering. As the eye moves left and right, you get this depth-dependent image shift, which is basically parallax. But it's small, and this is you have this variable resolution over the eye, where the fovea is actually only higher resolution, and in the periphery the resolution is lower, the visual acuity. So it's not clear if you even see this effect. If you dial it into VR, in a VR system, which is what we did with I think this was an HTC Vive Eye, which has a Tobii eye tracker, then it kind of looks something like this. So here's a conventional rendering where we track the user's eye. You can see the gaze point in red, but nothing changes as the gaze moves around, right? But if you enable ocular parallax, what you'd see is that there's this tiny amount of image shift in these stereoscopic images that corresponds to the gaze direction. And I just want to say again that what we're looking at here is a rendering of the image that is covering a very large field of view for the user. So even though the movements look fairly large on the right, in the peripheral regions, those actually have a very low spatial acuity. So the user perceives them as being very blurred because they only actually look at the fovea on the right? So we did a whole bunch of user studies, and I'll spare you the technical details, but the basic answers we found is that this ocular parallax is actually visible in modern VR displays that have enough resolution. Something on the order of 5 arc minutes is already good enough. That's still far away from retinal resolution, so it'll become more prominent as the resolution grows. And importantly, the effect size is the same as what we see for retinal blur. So retinal blur is this out of focus behavior, which people have studied in the context of the divergence accommodation conflict and other things. And it's really interesting that this ocular parallax actually is very visible. Does ocular parallax increase perceptual realism if you render it in? Yes, it can if the eye tracker is good. It's actually interesting that there is a lot of redundancy built into the human visual system. So even if there's some amount of latency, you'll perceive it, but it can still increase the perceptual realism. It is actually an interesting effect. What we studied in a follow-up paper was an indirect implication of this ocular parallax, which is that it impacts the interpupillary distance. So now, if I asked any one of you what your interpupillary distance is, many of you would probably know it because we're all geeks and we love VR and stereoscopic displays. So on average, the interpupillary distance is something like 64 millimeters, and it's typically fixed. You dial it into your headset optically and also in rendering. But what this ocular parallax effect implies is that as you verge at different depths, so if you look at an object that's closer, your eyes will converge. The centers of perspective will actually move towards each other, and the effective IPD changes. It actually depends on your gaze depth, and it changes dynamically. So again, the question is, okay, does it actually matter if my IPD is a couple millimeters smaller or larger? Well, if you run some simulations and you simulate the distortions of the disparities, which will only happen mostly in the periphery, because at the gaze point, the disparity is typically 0, then you'll see that there is actually quite a bit of distortion going on. The question again is, do you see that distortion? Does it affect your perceived depth? And again, we ran a whole bunch of user studies, both in VR and in AR, and there's a lot of going on the slide, so I'll just walk you through it. On the left, we did some experiments in VR where we showed specific patterns to users, and we measured the distortion of their depth perception. And turns out that for objects that are close by, the distortion is very noticeable. And this gaze contingent stereo rendering that you can dial in, basically dynamically adjusting the IPD based on your gaze depth, has a big effect, a statistically significant effect. For objects that are farther away, it doesn't really matter that much because the amount of parallax or depth distortion you'll see is small. So we found the same thing actually in AR, and there's again a lot going on, but I'll just point you to this plot here on the left. So for objects that are close, if you have a rendered stimulus next to a physical target, you'll get better consistency between these two across multiple different depths. So the depth will match between the two better if you dial in this ocular parallax rendering. It only matters really for objects that are close by. Again, for objects that are farther away, you don't really see a big difference. But what this means is if you want to build an AR experience where physical and digital objects are overlaid, and the digital object is supposed to be, let's say you have a little Super Mario that's jumping on your SIGGRAPH mug or something. If Super Mario is supposed to sit really on the mug, you have to get the depth just right. Otherwise, they'll appear to float somewhere else at a different depth. And in order to do that at close distances, you actually have to consider this gaze contingent stereo rendering. There are other effects like optical distortions and other things that you also need to consider, but ocular parallax is interesting and actually has a big effect. Okay, so many of the techniques I've been telling you about on the display side or on this rendering side require eye tracking. And I mentioned that eye tracking is something that seems to be solved already, but is not really solved actually. And we have looked into a couple of different directions, some modern approaches to eye tracking. I mean, then you would think, okay, we're just using neural networks. But no, there's actually a really elegant hardware solution to do eye tracking more robustly and at lower latency. Before I dive into this, let me just give you a general outline of eye tracking today. So today, we have wearable eye tracking systems or near eye systems. These could come from companies like Tobii. You can buy these. Tobii is supposedly being used in the PSVR 2 also that's upcoming. It's being used in a couple of commercial headsets that are starting to come out now with eye tracking. So Tobii is like one of the biggest solutions here. Pupil Labs is a small open source company that have been selling these eye trackers for a while. And, both of these types of systems run at maybe 120 hertz, up to 200 hertz, I would say. They're not very power efficient. So they're mostly coupled with VR systems that are tethered or that have a big battery pack on the back of your head. And they have accuracies somewhere in the order of 0.5 to 1 degree, which is, I would say, standard for eye trackers. On the other hand, if you talk to your colleagues who work on vision science and who are in the psychology department and who do human experiments there, they typically don't use these types of systems. They use things like iLink. The iLink is like a dedicated desktop desk-mounted eye tracker that costs you like something like $30,000 or so, and runs at like maybe 1,000, maybe 2,000 hertz. It's really fast. It's really accurate. People are typically strapped into these, chin rests, or maybe even have to go into bite bars so they don't move their heads. The accuracy is not much better than these near eye systems, but it's just a lot faster. So what is the speed? Why does it matter? Well, if you want to do things like gaze contingent rendering, maybe redirected walking, or foveated rendering, foveated compression, every millisecond that you can save on the latency will give you a huge benefit on the bandwidth. So it's actually really important to have this speed. But how fast does the human eye actually move? Well, I mean, it does move quite fast. Microsaccades reach up to 200 degrees per second. So the most subtle eye movements are actually pretty fast, and going up to 200, 300, 500 hertz makes perfect sense. Up to 1,000 hertz, you probably don't need a lot more than 1,000 hertz to capture most of the microsaccades. But I mean, if you want to get all these details, then you need to have a fast system. So in a paper that we published, when was it? 2 years ago now, we played it through, like, what if we want the absolute fastest eye tracking system that's out there, maybe thinking about like 10,000 frames per second or something like that, like to make sure that we really capture all the fastest movements, maybe beyond what people even know, because we don't have any eye trackers that are faster than 1,000 hertz. So maybe there are movements out there that are faster than that. So if you wanted to have something like a 10,000 frames per second system, and you capture images with 300 by 300 pixels that cover, a reasonably large region around your eye, and each pixel is 8 bits, well, that's a bandwidth of 7.2 gigabits per second that you need to read out, just the raw data, before you even have to process it. And if you look at this logarithmic chart here, where the green line is USB 3, I mean, we can't even use USB communication protocols to read off this data because it exceeds the bandwidth of that. So the iLink with 1,000 frames per second is somewhere around here. Tobii is here. it comes with a huge bandwidth, and bandwidth is not only problematic in terms of like systems engineering, but it also requires a lot of power. And power is probably the one big thing that doesn't work for AR, because it all needs to fit into the frames of your eyeglasses. Isn't there something more clever that we could do? Well, one insight that we had was that in a near eye tracking system, the camera is mostly mounted close to your head. And supposedly it doesn't move much with respect to your head. I mean, there's going to be some slippage, but maybe not too much. And what that means is, if we look at an intensity image, like the left one here, where the eye moves around, the only thing that really moves is the pupil and maybe the eyelashes when there's a blink. So this data isn't really sparse at all. You still need to read it out. But if you look at the temporal difference between successive frames, this is actually sparse because most of the image doesn't move. Isn't there some clever way to exploit this insight that, most of the things that move are just the pupil and maybe the eyelashes in this case, to reduce the bandwidth and the speed? And yes, there is, and it's called an event sensor. Event sensors are cameras that are regular CMOS sensors, but they have an integrated circuit in each pixel that only reports the difference, the temporal difference. It basically reports an event per pixel with its XY location and polarity whenever the temporal gradient of a pixel exceeds a certain threshold. And that is perfectly suited for this eye tracking solution, because what that means is, if we look at the same video that we just looked at now, is there's going to be a bunch of spurious events, but most of the events that we're actually recording are on the moving pupil and maybe on the eyelashes and so on and so forth. But most of the rest of the image is just blank. So we don't ever have to read out that data. This is an asynchronous thing, and the events are generated as they happen. So this isn't being read out at a fixed frame rate. And it doesn't have a fixed bandwidth. It's basically the events are just generated asynchronously and streamed off the chip. This is very power efficient and it's very fast. But it only works well for sparse scenarios. So now, the interesting thing is that there are some event cameras that actually are hybrid. They can read out frames, conventional intensity frames, at something like 30 frames per second or 60 frames per second, and then they can read out events in between these frames. So these are actually really interesting, and we built on one of these Davis sensors. You can see the data that comes off that sensor here. So this axis is time. We basically read out fixed frames in a certain frame rate, but then we get these events in between. So this gives us kind of the best of both worlds. We get the frames, we can run traditional eye tracking algorithms, localize the pupil, maybe the glints, and then we can use the frames in between to update that position in between the frames. We did this using an online least squares fit initially. So we do traditional, pupil fitting on the frames. We use the events, do an online least squares update on the updated model that includes the pupil, the glint, and maybe here the eyelid also. From that, we can determine the gaze point also. So that's indexing into a pixel of a camera or into the display. And that allows us to get almost continuous eye movements. You can see that here, the fitted pupil, we're going to stretch out the time and compress it a little bit. You can see that basically you get these nonlinear behaviors and motions in between the frames, even at this really fast frame rates, up to 10,000 frames per second. Now, is it useful to do 10,000 frames per second? I'm not saying it is, but we wanted to push the boundary and the frontier of the latency and the speed with this specific paper. Here's a demo that we put together where we have one of these eye tracking cameras in front of the user, and they're just following the mouse pointer. So you can see that, it works pretty well. There's some latency from the USB protocols and so on here, but this is generally very cool. Actually works. One of my former students, Amit, is doing this little test here. And we also even had a small event sensor that is sort of wearable. It's not really at the size of what you need for an AR/VR system, but it is getting closer, and these event sensors are getting smaller and smaller. So this is a really interesting direction, and we're actively pursuing that, and I'll tell you a little bit more about this later. But the thing is, I'm just speaking for myself now, but I think I'm speaking sort of for all of us, is that we love technology. We love to work on algorithms. We love to work on other types of technology, but people general people don't really care about technologies that much. They need experiences. They need cool things that they can do, really useful experiences that help them adopt this technology. So if we want this to be commercially successful, we can't just build technology for the sake of building technology. We need to engineer experiences. And this is where we need to think about what these systems actually do. And a couple of aspects of XR that I love include the following. Basically, augmented human performance. If you think about the single most successful wearable at this stage is actually eyeglasses. It doesn't do anything. It's just dumb. It has a pair of lenses in there and corrects your vision, but it's so useful that we wear it every day because it helps us see better. So this is just a pair of eyeglasses from Warby Parker. There are other emerging smart glasses that follow similar lines of thought. For example, Bose and others have these integrated sound systems here, so you can still use this as sunglasses or just regular prescription glasses, but they give you great sound as well. So you can take a phone call, you can listen to music, you don't bother your neighbor. It augments your hearing, basically. Or these Snap spectacles. Ray-Ban Stories have these cameras on there. You can snap a pic anytime. And so to some extent, they augment your memory because they allow you to capture photos in a more natural way than pulling out your cell phone or your SLR camera and taking a photo. So I think these are really great directions. I don't want to talk about augmented hearing and memory more, but I want to talk a little bit about augmented vision and eyeglasses because it relates to accommodation and focus, which I already touched upon earlier. And it's something that we can all relate to some extent. So normally we talk about people with normal vision. So what does that actually mean? So normal vision means that you're young, your lens in the eye can accommodate, that it can change its diameter. You can accommodate between a near distance and a far distance. Again, the accommodation mechanism, it's kind of like a pouch filled with a liquid lens that's being deformed by these ciliary muscles and the zonular fibers that connect them to the lens. But many of us are nearsighted or farsighted. And what that means is that our accommodation range is shifted forward or back. So I'm nearsighted, for example, so I can see my screen well, but I can't see the distance well. So I need to wear prescription glasses to shift this accommodation range back into the normal range so that I can see distant objects. But farsighted people can see the distance well, but not near. So they need to wear fixed focal lenses to shift it back. And fixed focus lenses are great to correct nearsightedness and farsightedness. There isn't really anything we need to improve on this. However, as we get older, we will develop presbyopia. Everybody does. Starts maybe around 45, 50, and is going to hit us all by the age of 60 or so. And what that means, presbyopia is a condition where you build up a protein in the eye, in the lens, that makes it stiff. It cannot be deformed anymore. And what it means is that your accommodation range is very short. You can only accommodate to one distance. It can be combined with nearsightedness and farsightedness, but the basic gist is that you can't see objects at multiple depths in focus easily. So for a normal person, for a person with normal vision, you can look at an object far away or close by. There's this autofocus mechanism of your eye that just adjusts. For presbyope, so somebody who's older, they can maybe see far well, but they cannot ever read anything. So what they need to do is they need to wear reading glasses, and reading glasses work well. They can shift our accommodation forward, and you can read well, but then you can't see the distance. So reading glasses only shift the focus to one specific depth, and that's challenging because you need to put them on and off. You need to, maybe you forget them, while you're driving. You can't simultaneously look at your dashboard and the traffic. So this is where progressive glasses come in, probably one of the most popular correction methods for presbyopia today. Progressive glasses have a varying focal power over the vertical region of the lens. So on the top part, you can see far. On the bottom part, you can see close, kind of the same as bifocals. The problem with progressives is that the field of view for any one distance is severely reduced. So you actually only have a small corridor on the top of your eyeglasses through which you can see the distance, and small corridor through which you can see the close distance. So you kind of have to use your head to align it with whatever distance the object is that you're fixating. And so progressives have problems. The natural solution is to just look at an object and the object coming into focus automatically. So, can we build some technology that kind of solves that natural, brings back this natural accommodation behavior? Well, the answer is yes. but we need dynamically focusable glass lenses in this eyeglasses pair. And there's a couple of options of doing that. There are physically movable lenses that are called Alvarez lenses. They're two pairs of lenses shaped in a way that creates a lens with a specific focal power where the focal power shifts. We can use liquid lenses that are basically operates like the lens in the eye. You can apply some pressure here on the side, for example, using piezoelectric motors that deform the shape of the membrane to focus at different depths. And there are also emerging liquid crystal technologies that are kind of similar to LCDs, but that just change the refractive index of the material dynamically. So there's a couple of different options of dynamically changing the focal power of a lens. And the question is, is this really useful? Does that make sense? Does it actually improve people's vision? So we started prototyping with some of these ideas. Here's an early prototype. It looks more like a pair of ski goggles. We used large liquid lenses. We used a stereoscopic eye tracker from Pupil Labs. In this specific prototype, we had a depth camera on there from Intel also. So large focus tunable lenses, they're kind of affected by gravity because they're liquid. So, we need to have some correction mechanism for that. So this is more like a research grade prototype. This is not something you'd actually use. The important thing is you also need to be able to correct for myopia, hyperopia by putting fixed focal lenses in the front. So we call this autofocals because it's an autofocal mechanism. And what it does is basically you track both eyes. You estimate the gaze depth by estimating the divergence angle between the gaze directions of the two eyes. And if you look at an object that's close by, your focus lens is close. If you look at an object that's far away, like this Renderman teapot here, the box and the teapot is close, the box is far, depending on what you're looking at, the lenses will automatically adjust the focus. And you get the full field of view, right, at this focus. There's some aberrations here on the side which come from the eye relief between the camera and the lenses. If you actually put it on your head, you don't see that much. Okay, so we ran lots of user studies. We showed this at eTech also actually in 2018, tested a lot of people there. And we found that it significantly improves the visual acuity over multiple depths compared to monovision and some prescription methods. But it importantly improves the task performance over progressives also, because you can basically look at small objects at different depths using your gaze only. Whereas for progressives, you have to always align your head, and that takes time, and it's not as efficient and not as natural. So even people who typically wear progressive glasses, we were able to improve their task performance in visual tasks using this first autofocus prototype. So this is a really great idea, I think, to help people see better. It doesn't use a display at all. And that's a slightly different paradigm from, I think, how most XR companies think about VR and AR today. Typically, we start with a big display that has all the different features that we want. And then over time, we try to miniaturize it, make it smaller and smaller. So these are some examples here, right? And we hope at the end of the day, we have something that's small and has all the features in it. But I think another way to think about it is we just start from eyeglasses because they're so useful as is already, and we just add the most useful features to them, maintaining the style and the form factor of the eyeglasses. So we could add some sound features, we could add some vision correction, or help people see better. And eventually we can maybe add a display, because smart glasses are more than just the display. And I think the form factor, size, and power constraints are more important for people than some of these systems, because I'm having a hard time imagining people running around on the street with these types of systems. So one startup I co-founded with some of my former students is called Zen Labs. And in that context, we are actually developing all-day wearable eye tracking that is super robust and super low power. So I'd be more than happy to chat with you if you're interested in this technology. So it's coming. It'll take a little while, but we're going to have very fast, super low power, absolutely robust eye tracking in these tiny form factors soon. Okay, that concludes my talk. I told you a little bit about some of the recent projects that we've been working on AR, VR, and wearable computing in general. My lab is actually the computational imaging lab, so we work on a couple of different topics, including computational cameras, single photon images, imaging, using AI to redefine applied optics. We work on computational microscopy, neural rendering, These are all other topics that I didn't have time to touch upon today, but lots of really exciting things happening. And I hope this was interesting and informative to some of you. There are lots of challenges on high-performance graphics in this space of systems engineering or display systems engineering. I'd like to thank all my students and postdocs, current and former, and also our sponsors. Hopefully we have a couple minutes for questions. And thanks again for the organizers for inviting me. This has been a pleasure to be part of this conference.
Thank you so much, Gordon, for a wonderful talk. It's amazing to listen to you each time, and thanks yet again for showing us the technologies that will drive the entire stack of future XR. This is amazing. We actually have quite a bit of time for questions, like 10 minutes. And while people are either typing it up or stepping up to the mic, I have quite a few questions for you. These are some of my favorite topics as well. So I'll start with eye tracking. Like you, I've also been frustrated at the pace at which that technology has evolved and improved to become usable in VR. And one thing I found while I was working with, at least with foveated rendering, was that the end-to-end latency of the system tends to be dominated by the non-eye tracking parts, namely the display, at least in the VR applications. And I always kept worrying that even if I had an infinitely fast eye tracker, I would still have like 30 milliseconds before I can show something based on the tracking. So do you feel like the display technology needs to evolve in some way in tandem with, or maybe even the algorithm should be involved in tandem with eye tracking?
Yeah, this is such a great point. So, and this is what I tell my students in the class on VR that I teach is like VR and AR is a systems challenge. Like it's always limited by, the bottleneck may be somewhere, whatever the weakest link is, this is how good your system will be. And that's why it's so important to consider all of these aspects. And those include rendering, hardware acceleration, displays, but also the human eye and the camera system. Everything has to work together, right? And that being said, like conventional cameras, have lots of latency and lots of power actually. So I think these event sensors are mainly useful for bringing down the power, right? That this is mainly the main benefit. Yes, they are also fast and they're also robust. So these are great additional benefits, but I think it's mainly there for power, but it's hard to give an exciting talk about power saving. So I didn't really emphasize that aspect, but you're right. So let's think about the display. There are many different displays that are actually being used today. So, LCD is maybe the dominant technology for most monitors. We don't really use it for VR that much, but in an LCD display, you have a fixed frame rate, maybe 60 hertz or something like that. But the image is actually being scanned out sequentially over the LCD panel, and there's no way for you to change a pixel until your write-out mechanism comes back. Maybe NVIDIA has a couple of tricks up their sleeve, obviously, but it's actually challenging. OLEDs can be fast and have low persistence, so they can actually drive pretty fast, and they're really useful for VR. But there, the limiting factor will be the backplane. The backplane and the electronics that are actually driving the OLEDs, they will be the limiting factor because they're going to have to minimize the bandwidth, otherwise the power goes up, and you need to have smart backplanes. And that is a key requirement for, I would say, VR. And some people have been working on this. So, for example, Compound Photonics has publicly talked about for a couple of years about their smart backplanes. And what that means is that you can directly dial in the eye tracking location, for example, the gaze position into the backplane, and you have not just a foveated rendering mechanism, but a foveated backplane if you want. So you can, directly turn on at a high resolution the backplane, but you have to synchronize it with the GPU. So everything has to be done in harmony. Now, OLEDs aren't really all that useful for AR because in AR you have a waveguide, and the waveguide is so optically inefficient that you only get about 1% of the light coming out on the other end. And an OLED is limited in the peak brightness that it can do. So there we need micro LEDs, and this is something that we've worked on at Raxium, and other companies obviously are working on this. But there again, the limiting factor is going to be the backplane. So we need backplanes that support that. And then thinking about laser beam scanning, so lots of developments on AR are out there at all the big fan companies, obviously, and some of them are thinking about using laser beam scanning, and laser beam scanning is basically using a waveguide that's very thin, using a little MEMS mirror that scans a laser, basically point by point, like raster scanning the point, like your good old CRT monitor. The thing is, again, like if it's a sequentially scanned display, there isn't anything you can do in terms of saving the latency, right? It's not like you can steer this laser to arbitrary positions. It's not like a vector display. It has a fixed oscillation rate, this mirror, right? So different display technologies are differently amenable for reducing latency. And again, it's a systems challenge that includes many factors, including form factor, power, latency, and many others. So there's so many different components that have to come together and all work in harmony that it's challenging. Sorry for just babbling on here in your simple question. I think it is a complicated issue, is what I'm saying, and all these components have to work together. Yeah.
I think
it's the key question.
Yeah, definitely. So there are a couple more questions on the board. I think the first one was, Canon seemed to have very mixed results with the eye tracking for autofocus point in the R3, according to reviewers. How much difficulty do you expect in getting a robust solution in the field?
Sorry, can you
so Andrew, is it possible for you to elaborate your question? I don't know what you mean. Well, while he might step up to the mic, let's me talk about the next question. It says,
okay, I mean, I think I know what you're talking about, but when you think about eye tracking, there's a couple of different aspects to it, right? Like if you think about a single eye, typically, first of all, we want to estimate the pupil and maybe the glints. From that, we get a model, we get the gaze direction. And so indexing from the eye tracker into the pixel of a display is a challenge because you need to be robust for slippage and so on and so forth. But I think what he's saying with autofocus point is like binocular eye tracking is also, you need to track the gaze direction of both eyes and then triangulate it and get the vergence angle between them, right? That's actually very challenging because, what we said earlier is like you have a accuracy of like 0.5 to 1 degrees maybe for each eye, which means that there's actually quite a bit of wiggle room for each eye, and getting the gaze angle or gaze depth robustly is challenging. Yeah. Is that what you're referring to, Andrew? Or
they might do better if they use both eyes. No, I really just meant, so Canon used to have some old film technology where they tried to estimate where the eye was looking in the frame and use that to select between their options of autofocus points. And they've resurrected that recently for the R3. And some reviewers are saying this is wonderful. It's the most interactive, automatic way of deciding where to focus in the frame. It's completely going to revolutionize things. And quite a lot of other reviewers are saying it doesn't work. I can't get it to work. You have to calibrate every 5 minutes, arg. So I'm just wondering how
calibration is challenging, right? Slippage. I mean, you can typically, the way these eye trackers are calibrated is you have this 9-point calibration method that is happening per user, per use case, right? You show 9 points. You build some kind of a lookup table, and then you assume that the eye doesn't move with respect to the screen, and you can track the gaze, right? It's unrealistic because if you have a wearable system, there's going to be some slippage. If you have a monitor, you have to keep the head fixed. That's why people in these vision science communities use headrests to keep the head stable, or even bite bars where you have to bite on something just so that your skull doesn't move. So, building something that's robust to slippage that's challenging and sort of independent challenge from everything I've talked about. It is a big challenge, but I can't say it works or it doesn't work. There is a lot of smartness going into that, and I'm sure we'll see good things happening very soon. Like if you can get gaze, so glints and pupil separately, for example, there's some robustness built in, and there's a lot of interesting ideas out there. But yeah, I would say it's possible, but it's very challenging, actually.
Yeah, cool. I look forward to seeing the crossover of research anyway. Thank you. Cool talk.
Next question, I think it's also a systems-y question. Thanks for the talk. Some perceptual effects, the ones that you described, some of us will never think of and require a lot of research and knowledge, just to research and various different science domains knowledge. Do you think every engineer working in this space would need to be familiar with those, or is there a way to decouple it from such systems software design perspective?
I mean, yes, again, like AR VR is a systems challenge, but so is computer graphics, right? Like if I remember my first computer graphic classes many years ago, too many years ago, I mean, we learn about human vision, about color perception, about radiometry, about physics. there's many different components to it, and it sort of became a thing in graphics where we have pretty standardized courses that we can take as undergrads to help us understand at least, Vision Science 101 from a very high level perspective. And doesn't mean every software engineer has to become a vision scientist, but I think it's good to understand that, the fovea has more photoreceptors than the periphery, and that there's some drop off. And I think, that we have four different photoreceptors in our retina. So it gives us like trinocular vision or day and night vision. So very simple concepts from vision science, I think, are not only exciting, at least to me and to many of you also, but also something that I think people should know about. But it's a different level of abstraction. That doesn't mean you have to be a vision scientist to do that. But I think, again, XR is a systems level challenge, and be able to at least understand the basic concepts at a certain level of abstraction is required to really push it forward. Maybe not at every level of an engineer, but if you really want to push the needle, you need to consider multiple different areas, and working in interdisciplinary teams at least is sort of important, I think.
Perhaps there's also opportunity for sort of computational models or systems that are like, intermediate black boxes for one community to use from the other, to sort of
absolutely
unblock each other.
I mean, if you think about what vision science does as a field, is they build models, right? It's actually a really boring field if you think about it. Once you have a hypothesis, you have to run many, many user studies, capture lots of data points, fit some model to it. And that's what vision science is published. And then, we're sort of it's beneficial for us because we can just take that model and then apply it and build really cool rendering and display technology around it. And I mean, some of us also more on the vision science side, or at least try that a little bit. And I think some of us get more excited about it, others get less excited about it. But I think the important thing is the interface between the fields, and these are typically these mathematical models that will model your, the visual acuity over the retina and things like that. And I think, I teach these things in my VR class, and even the undergrads understand at least the basic concepts of that and play around with it a little bit. So I think that's about the level of abstraction that I think every engineer who works on XR at least should understand them. But again, you don't need to understand all the different types of cells or all the different nuances. I mean, this is beyond what I understand too. Like, I have a lot of colleagues here in vision science who, for example, like one interesting aspect is that, the photoreceptors actually mechanically deform by a few nanometers whenever they fire or something. Is that important for graphics research? I don't know, but I have some colleagues who built interferometric measurement systems for the retina who study the mechanical deformation of photoreceptors when they fire. It's just interesting, but I don't understand it as well, right? Like, I think it's fine.
Fascinating.
Yeah.
There's one more question, and I think I have like 10 more questions, but I think we're running out of time, and we're eating into our break. So I'll take one more opportunity to thank Gordon for once again spending time with us and talking about all the awesome stuff you've been working on and what lies in the future. So thanks so much, Gordon.
Thanks for having me.
We will now have a break for about 1 minute.